Good morning, lovely Year 13s. Right, buddies, here we are again in the lovely world of online learning. But that's okay, though. We've had experience with it now, so now we're amazing at doing the online learning, so this should be really good. And I'm really pleased to tell you I get to teach you some pure maths for a change, and our very first unit that we're going to do together, of two, is just differential equations, so please put the title Differential Equations. Now, this unit is really cool. The first lesson in it that we're going to do right now is a little bit fiddly, but it gets to be really an awesome unit. I really liked this unit when I've got myself all prepped for it, so I think that you will as well, I hope. But yeah, here's what a differential equation is, buddies. Essentially, if ever you just get an equation that has a derivative in it, then it is a differential equation. So if you had an equation that had a dy dx in it, an f prime of x, an x dot kind of thing, just to show it's like a first derivative, that's kind of a physicsy way of writing it. Yeah, that's what you've got. So that's what a differential equation is. They come in orders, so the first unit that we're going to do is first order differential equations, and that means that the highest derivative is of order 1. So there would be a dy by dx, but there wouldn't be a d squared y by dx squared, as that would be a second order, because you had to differentiate twice to get to it. Cool beans? So we're going to do first order differential equations first. Cool. So what I thought is we could just bust through a whole bunch of questions and see how it goes. It's really calculus-y, which is brilliant. I really like that about it. And yeah, there's one little skill that I'm going to talk about in a minute that I just don't know if you've learned yet. It's in regular math, but I think it's at the end of year 13. So yeah, you'll have to tell me in the Google Classroom there if you've learned it or not, or if I should teach it to you. So here we go. Anyway, first ever question. Here's what we've got. It says, a simple model of the atmosphere above Earth's surface is a perfect, it says that the atmosphere above Earth's surface is a perfect gas at constant temperature. This means that the pressure, P, at any point is proportional to the density, rho. That's great. The one that looks just like P. That's brilliant. Yeah, but anyway, yeah, it says that the pressure is proportional to rho, which is a Greek letter. The rate at which the pressure decreases with respect to Z is proportional to the density, okay? So the rate at which this decreases with respect to Z is proportional to the density, which was rho. And there we go. The question says, use this information to find an expression for dp dz in terms of P. Okay, so it looks quite awkward and it looks quite horrible, and this is what I mean, like this is the fiddliest part of it, but it's not too bad actually. We can just, yeah, you'll see, it's not too bad. This is fiddly. It gets really cool, but this part's fiddly. Okay, here's what I say we're going to do. We're after dp dz. Essentially, it's asking us for an equation that has dp dz as its subject, with p as its kind of independent variable, as the variable that's floating over on the other side. Okay, so here we go. We got two bits of information, which is kindly laid out for us with bullet points. It says the pressure at any point is proportional to the density. Okay, here's what it's telling us. I'm going to call this, I don't know, 1. That can be 0.1. Okay, on 0.1 it's telling us this. It's saying that pressure, P, is proportional to density, which is rho, which I'm not very good at drawing. So oh, this is going to be a nightmare, I can tell you straight off the bat. Okay, I'm going to really curl it. There you go, there's a rho, there it is. So P is proportional to that. Now, unfortunately, that's not an equation, but my lovelies, you know how to turn that into an equation from GCSE. That means that P is going to be proportional to, and it's usually like K times the rho. See what I mean? So it's, oh, not proportional, it's equal to K times rho, because that means that we've switched it from being a proportionality, which is not super useful to use in terms of solving, but is super useful to use in terms of ratios and getting graph shapes and stuff like that. We switched it into an equality, which is useful always. Okay, now I might know a little bit of something here, so I'm actually going to call this K1. Okie doke, buddies. Sweet. That's all we can do with that. Okay, equation 2. Now, here's where it gets calculus-y. Here's where it's a bit funny. It says the rate at which pressure decreases. Okay, what is the variable that matches up with the rate at which pressure decreases? Well, I'm just going to tell you because I'm not sure if you will know. I hope you'll know. Maybe you already do know. But we're talking about pressure decreasing, right? It's going to decrease over with respect to height, okay? The rate at which pressure decreases with respect to height. So here's what it's actually telling us, buddies. It's telling us dp dz. That is dp dz. Whenever you get these little d's in, the derivative things, this is the derivative of p with respect to z, whenever you get these little derivative things in, it's talking about a rate of change because that's what a derivative is, just like how dy dx represents gradient in the same, which is how far y changes with respect to x. This is how pressure changes with respect to height. Does that make sense? I hope it does. So that's dp dz. And it says that it's proportional, so proportional to the density, which was rho in the previous bit, and that's what you've got. Now, there's one other trick to it, and that's this word here. It says it decreases. Now, because we're dealing in proportionality here, it's kind of like correlation in stats. If it's decreasing, it's going to have a negative gradient. So this is what we've got. Okie doke, a negative gradient to account for the decrease. Cool. Switch it to an equation. That means that dp dz is going to be equal to, and this is why I put k1 in the last one, because we need a separate constant. It's going to be minus, so keeping that red minus, k2 times rho. Cool beans? Well, guess what, buddies? Bish, bash, bosh, you've done it. You've got two equations here. You can put those bad boys together, and that's what you've got. So this can be equation 1, this can be equation 2, and what we're going to do is we want a dp dz in terms of p. Actually, before we do this then, let's get rho as the subject of this one. What do you reckon? Because, yeah, I don't like rho because it looks like p. But anyway, here we go. That means rho is equal to p over k1. Cool. Let's call that equation 1. Because then all you have to do is 1 into 2. Cool beans. That one into that one. And you're going to get this. dp dz is going to equal negative k2. And then in here, you're going to be p over k1. Happy days? Which means that dp dz is going to equal, now p is a variable and k is a constant, right? So I'm going to leave my p chilling out there, and I'm going to have this as minus k2 over k1. And then the thing that I'm going to get with that then as well, my buddies, I don't like the way I've written that, but that's okay. You know, we didn't know k1 or k2. They're both it's like k1 and k2 are both unknown kind of constants. Here's what you can do. Whack them together. This is something that you always are going to do with differential equations too. Let general k equal k2 over k1, because then you get a nice simpler answer of dp dz, and that's just going to be negative kp. And that is the answer to your first ever differential equation question. Now, we didn't even differentiate in it, but it was just a matter of laying out proportionalities. That's what that one did. Cool beans, my buddies? Sweet. Right, so on to the next one then. Here is what we've got. It says, a little bit harder this time, that the volume V of a spherical raindrop of radius r, oh, here's a keyword, is decreasing due to evaporation at a rate that is proportional to its surface area S. Okay, now it wants us to find an expression for dr dt. So that's our end game, that is. We want to know what dr dt is. Right, here's what I'm going to do. Here's my thoughts when I get to these fiddly questions. I say to myself, what is the actual information that is given in the question itself? And the information that's given in the question itself is it says that the rate that the volume is decreasing is proportional to the surface area. Okay, it's on about a rate, so it's not going to be v, but it is going to be dv and dt actually. dt, because it says it's evaporating, it is with respect to time that volume is changing. Now it says that that's proportional then to its surface area S, but also is negative because of decreasing. Now I think that's the fiddliest, so I'm not sure if you think that's the fiddliest or not, but that to me is the hard step. Yeah, sweet. Now let's bish bash bosh it into an equation. That means that dv dt is going to be equal to negative ks. Now, essentially at that point, I could swap s out for maybe the radius or something like that, but I'm just going to say that this is a bit funny. After dr dt, there's not even an r in this, and if I were to put an r in this, it wouldn't be a dr dt, it would only just be an r. Should we just do it? Yeah, okay. I'm just going to do it. Let's just do it, okay? Because you guys know that if there's a sphere, you know its volume is actually 4/3 pi r cubed, and its surface area is actually 4 pi r squared. I don't know if you do know that, but that is true. It's one of those ones that you didn't have to memorize at GCSE, but actually is quite useful. Do you know what? I think I'm going to veer off track a bit here. I'm actually going to whack that in there just to show you. I'm going to swap s out for 4 pi r squared, okay? That would mean that dv dt, so but s equals 4 pi r squared, which means that dv dt is equal to minus, I'm going to put the 4 first, 4 pi k r squared. Cool? Happy days. So all I did was I put the 4 pi r squared in for that. Now, you see, the only reason I did that now in this step, because there's a tidier way of doing it, but I put it in this step, just so you can see I can't actually get dr dt because there is no dr dt. I couldn't differentiate this because if I differentiated it, I'd be left with the dv squared, and that's awkward as well. So that's not cool. So now we have to go on to a different fact. Do we know anything about volume in a sphere? That's right, we know though that the volume in a sphere is 4/3 pi r cubed. Now, here's where we're going to crush this majestic thing, my lovelies. If you look at this, because this is true, the volume is always given by that if it's a sphere, what we can do if we want to get a rate is we can differentiate this with respect to time. Okay? Now, this is the topic that I was on about earlier. I'm not sure if you use this, but this is called implicit differentiation. If you go to each variable on its own, so look at the v, and you can differentiate it in its place by respect to another variable. So if I differentiate v with respect to t, it actually becomes dv dt, right? The same way as if you differentiate y with respect to x, it becomes dy dx. I don't know if you've learned that yet in year 13, but it's definitely a year 13 topic. Now here's the next thing then, buddies. On this side, 4/3 pi r cubed. If you differentiate that, 4/3 and pi are both constants, so they just chill. And what happens is 4/3 gets times by 3 because that comes down in the power. So you're going to be left with 4 pi r squared. But then here's the implicit differentiation. What does r differentiate to with respect to time? So we just differentiated the r itself. Now we're going to go inside and differentiate the variable of r. What does r differentiate to with respect to time? Well, actually dr dt. Okay, so you're going to have to tell me if you've not learned that yet, okay? But that is how it works. It's essentially chain rule. So I taught this like, say that the 4/3 wasn't there. Say it was just, I'm just going to go through it really quick, okay? If you had r cubed, if you differentiated it, it'd be 3r squared, right? But the thing is, if then you go in and differentiate r, r itself becomes dr dt. That's what I'm using there. It's chain rule. Okie doke. Cool. So that's it. That's what we've got. And now look, that's wicked because dr dt is in our equation now. So beautiful. Well, what are you going to do now? Well, the same as last time. You're going to whack them together. Cool. We're going to go 1 into 2. Because when you do that, you're going to get minus 4 pi k r squared is going to equal 4 pi r squared dr dt, which is what we want the subject to be. Now there's a lovely amount of cancelling here. 4 goes with 4, pi goes with pi, k doesn't go anywhere, and r squared goes with r squared, which means at the end of the day, you are just going to be getting, where's my pen here? You are just going to be getting that minus k is what's left there is equal to dr dt. So I'm just going to write it the other way, which means dr dt is equal to minus k, which is the answer to this question, okay? That is the answer to this question. Now, it's got meaning in terms of physics. Dr dt then is just a negative constant. So, because remember, k was just the thing we introduced over here. It's just a constant. It's just a whole number. So it might have been a 2. So dr dt meaning minus 2, it would mean that the radius was decreasing at 2 centimeters per second. So in other words, you don't have to know this, but this means that the radius is decreasing at a constant rate. At a constant rate. At a constant rate. Now, rate. You might be thinking to yourself then, this actually has really good real-life applications because, I mean, this is how you can get formulas in physics. This is how you can do lots of stuff in science. And so, look at, we're doing science and maths. How exciting. Woohoo! Okay, less fiddly now before we get to the cool stuff. Okay, 2 more things you gotta know. There's 2 special things we're gonna talk about, and we're gonna do these a lot when we get into differential equations proper. There's 2 types of solutions to differential equations. There's what's called a general solution, and they are the ones that have a plus c in. Just like the same as an integration, it's called a general solution in integration when you've got the plus c, and it's called a particular solution when you know what the plus c is. So you could have like a plus 2 or something. Cool beans? So a general solution still have the constant in, and a particular solution is one particular curve. Now if you're to graph that, which I've tried to show here, I'm just pretending that these curvy like cubic graphs that I've drawn are a general solution. See how there's a whole family of them? Because we don't know what c is, and all c is affecting is kind of the y-intercept in this case, because it's at the end, right? Like if you go plus 2, that's a shift up of 2. If you do like minus 3, it's a shift down of 3. So you get an infinite number of parallel curves that are the general solutions. So these are all the blue ones. But say I told you that when x is equal to 4, y is equal to 6, well, that will let you lock down which curve you're on and figure out which c you are, and the particular solution would just be that one red one, which is part of the family of curves. Cool, cool, cool beans? Right, so here we go. This is less fiddly now, so you're going to like this. Okay, these verify ones is just a matter of, like, manhandling it with calculus, so it's cool. It says verify that y equals ae to the minus 3x is the general solution to this. Okie doke. Now, differentiation is just verify, so you're just trying to show that they're equal. And differentiation is way easier than integration, right? So we're definitely going to start with this one, okay? So we're going to consider the equation, okay? And we're just going to see that one can become the other. That's all we're trying to show, is that one becomes the other. So here we go. Y equals a e to the minus 3x. Now the thing what we're trying to get to is dy dx. So what are we going to differentiate with respect to? Well, yeah, x with respect to x. Cool? So dy dx then, oops, dy dx, it's just going to be this. A is a constant, so it's chilling. So you're going to get a again. It's just going to chill. E to the 3x is going to differentiate to e to the 3x. But then you go into the top for chain rule, you go into the power, and you get a minus 3 as well. So this is minus 3a e to the minus 3x. Please again tell me in the Google chat if the way I'm doing this is too fast or you've not done this to the right step, because I'm skipping differentiation steps kind of in what I think is your interest, but I might be making it harder for you, which I don't want to do. Cool beans? So anyway, dy dx is equal to that. But oh drat, that doesn't equal this. Oh no. Oh dear, that doesn't equal this though. So our dy dx is equal to that, but it's not equal to minus 3y. Until you spot that y is equal to ae to the minus 3x. So actually, it is equal to that, because check that majestic bad boy out right there. That is that. Cool beans? So you can swap. That means that dy dx is equal to minus 3, which is chillin', but ae to the minus 3x is y, which is what we set out to do. Bish bash bosh, no trouble at all. Absolutely smashing it, so no problem. I like it. Yeah, so that's it. Cool. Oh yeah, I was going to show you this as well. So that's the general solution. I'm just going to show you what that looks like because the textbook had a cool graph of it. See how it said, or do you see how before I highlighted it, I'm going to erase the highlighting actually. The A here, my buddies, was a constant, the capital A that it's being times by, it's just a constant number. So here's its family of curves. This is the general solution of that exact question, okay? So you can tell, solution, you can tell for this one that regardless of what A is, as x gets big, it becomes e to the power of negative something big, which means it's like 1 over something big, which means it tends to 0 the further out to the right that you go. And then the a just determines which curve it's on. So if a was a negative number, it'd be, or sorry, if a was a negative number, it'd be up, and if a was a positive number, it'd be under because of the -3. So there's the entire family of curves that it goes to. So isn't that cool? I think it's cool. Right, last one for us to try. Here we go. Verify that this is the particular solution of the differential equation that satisfies this condition. I'm going to just try to give you an instruction on how to do this, and then you can try it. But then, yeah, that's what I'm going to do. So here's what you should do, buddies. Same as we did this one, treat it exactly the same way. It doesn't matter that it's a particular solution yet, but start off just by showing that they match up in terms of general solutions. So start by differentiating this and see if it does equal that. Okie doke. After you finish that, then check your answer and confirm that this does actually work. So if you want to pause and try, do it. Go. Okay, buddy. So hopefully you've had a little bit of a try there, and I'm going to do just what I told you. So let's do the, let's start with the equation. And the equation was v equals 20e to the minus 2t plus 5. Now, the thing that we're trying to get to, and I'm starting with the equation rather than the differential equation, because differentiation is easier to do than integration. So here we go. Let's get dv dt. Okay? Because that's what we're trying to get. That's our goal. That's the bottom equation. Now, I'm going to skip steps, so I hope that you're okay. This is going to be minus 40 because of the minus 2 from chain rule, e to the minus 2t, and then the plus 5 is just going to go, actually, isn't it? The plus 5 will just be gone. Okie dokie. Now, we don't yet have... What are we going to do here, my buddies? Okay, we don't yet have this at the bottom because we've still got e to the minus 2t. So actually, I am also going to start with the differential. What am I going to do? Am I going to start with the differential equation? Would that be good? Yeah, I am going to. What's going to happen though? I don't know. We'll find out soon. dv dt is going to equal 10. Oh, I know what I'm going to do. I got it. Okay. I am going to start with this one because I can't keep working with that one because I've exhausted my equation. That's as far as I can get with the v1, right? So I have to move to the other. Take away 2v. Okay. Here's what I'm going to do, my buddies. There's the differential equation. I'm going to, because I'm trying to get the dv dt here on the differential to equal minus 40e to the minus 2t, but this has a v in, right? So since that's got a v in, I'm going to sub that in because they're not of the same equation, right? This has come from there and that comes from there, so I'm going to treat it like a simultaneous equation. So let's do that. But v equals, that is going to work, I can see it already, e to the minus 2t plus 5, which means that dv dt is equal to 10 minus 2, open bracket, 20e to the minus 2t plus 5, and then you're going to get dv dt, which equals 10, take 40e to the minus 2t minus 10, which, oh my gosh, dv dt is equal to minus 40e to the minus 2t, which, oh my word, is confirmed. So there you go, confirmed. So same. So V is the general solution. The general solution. Okay. Because it worked, right? Because we fiddled with them both and they ended up being the same thing. We treated each equation separately and they ended up coming together. Now we've got to also just satisfy the particular part. So we've just done the algebra part, but now we've got to do the conditions. So now we also have to verify this. We have to verify that when v is 25, t is 0, or when t is 0, v is 25. We need to do that too. and that confirms everything. Well, all we have to do there, buddies, is hit up that top equation. So it's going to be, well, let's just use the t equals 0 part, so that'll be easier. So try t is 0. Try equals t equals 0. Now here you go then. It's going to be v, well, because it's this equation, v equals 20 e to the minus 2t plus 5, which means that v equals 20 e to the 0 plus 5. Anything to the power of 0 is 1, so this is v equals 20 times 1 plus 5, which means v is 25. Bish bash bosh, which is what it was supposed to be, so that's also confirmed. Cool beans? Now, that's fiddly, that's not proper differential equations yet, but I think that the reason why this is included is because this popping equations into each other and knowing how to do this implicit differentiation and knowing when to differentiate and stuff like that is going to be super important soon. And that means next lesson we can do the fun differential equations. So here you go, my buddies. Try some. It's just practice. You need to just do a few, okay? That's how I did it as well. Just do a whole bunch of them. It'll be wicked. It's page 182, question 1 to 16. Do a mix based on how you feel. So do question 1, find that really easy, then jump to question 7, then find that easy, then go 15, 16, 7, or like 15, 16 or whatever. See what I mean? Pick a mix that suits your ability. That's it from me. Yell at me in the chat if you want to talk about anything, and that'll be it. So, nice one, buddies. See you next time. Bye, lovelies!